Let's see. Hello, everyone, and welcome to our webinar. We are here a little bit earlier, so as you come, please introduce yourself in our chat. Let us know where you're from, and we'll start right on the hour. So, where's my chat? Here we are. Yeah. So we see people coming through. So we have been debating on whether we want people, there we are, people to, whether we want any music while we're waiting. If you were to add some music to that, what kind of songs would you play?
You got me stumped right off the bat.
Yeah.
Nice. All right, so we have people coming from the US to begin with. Missouri, Illinois, no music. Okay, fine, no music. I was thinking more about holes, the planets, something appropriate. Houston, binocular visual variable star observers. Hi, Michael. The very first star I've ever observed myself with my own equipment was Chi Cygni through my binoculars. So an awesome LPV.
You started out right.
I started, oh my goodness, and a week later it had changed. So I was like, oh, it really changed. It's not just me. So exciting. Hi from Nebraska. Hi to Nebraska. Hi to the UK. Good morning, good afternoon, good evening to everyone as you're hearing us. Hi, Brazil. Very nice. Cool. We're at 71 participants and increasing. Hi, South Africa. Very nice. Hi, Andres in Germany. Arizona. Oh, how nice. UK, India. Hello, namaste. It's really cool to see where people come from. Hello, France. Hola, Argentina. All right, we have 5 more minutes until we will start. Bolivia, Bavaria, Maryland, India. Betelgeuse, post-solar conjunction. Are we going to talk about Betelgeuse today, or we're going to leave it for the PEP session?
Yeah, I think we'll leave it to the PEP session. I don't have anything planned for it.
So
like you think LPVs, and we're going Myras today.
Yeah. Betelgeuse too big.
Hello, Venezuela. Yeah, we'll talk a little bit about Betelgeuse in 2 weekends from now, I think.
Oh, good.
Yeah. Just outside the Kuiper Belt? Oh dear, that's far. Sure.
About expanding our reach.
Yeah, we're taking over the solar system at least. Wonderful, wonderful. Hello, Wales. Hello, Venezuela. Where else do we have people from?
Oh, this is amazing.
Right now we have 112 participants and the number is increasing.
Amazing.
I see Finland. My daughter is there.
Ah,
Ah,
Turkey, Chile, Hotlanta, India, all over. I like it.
all over. Oh. New Mexico.
Colombia, Prague.
We have a question, Leon, about your daughter. She's studying in Finland.
You're on mute, Leanne.
You need to unmute yourself.
She is researching in Finland. She's an expert on Scandinavian languages, fluent in Finnish and Swedish and Icelandic.
Cool. Spain, Arizona. Hi, Jay. Good to see you again. India. It's great to see some known old friends and make new ones. I love this. I really love this. All right, let's, I'm going to give a couple more minutes, Rich, if that's okay.
That's fine by me.
Wonderful.
Settle in.
England. Oh, I love this. Wow. Mumbai, midnight coffee. Oh my goodness, so wonderful to see people from all over the world. Solar seminar is coming up. Jay, you should come back, but stay for this one. This one's really awesome. All of them are awesome.
Our son will eventually be an LPV.
True.
If you're patient enough.
It's going to take what? Like
11, 12 billion years maybe? I mean,
yeah.
I think it's about 7 more to go. So
for now, right. So it's going to be post-coronavirus. We hope.
oh no.
Oh yeah, you can't believe I said that, right?
Oh, no.
I think we can get started. We have more than 150 attendees. So welcome everyone, and thank you for joining us today. This is the 5th webinar of our series, and we're going to be talking about long period variables. And I am joined here by Rich Roberts, Abby Wagner, Michael Stroh, Margarita Karowska, and Leanne Wilson. We have a very exciting program for you with wonderful presentations. I would also like to acknowledge and thank the Boyce Research Initiative and Education Foundation that is supporting these webinars. Boyce Astro provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools to learn how to perform observations, conduct research, and publish the results in scientific journals like the Journal of the AVSO. Boyce Astro has been a very close ally and partner to the AVSO for years, and it's a pleasure that's supporting this webinar. I have their webpage here, so feel free to check them out to see what kind of work they're doing. They're preparing the next generation of scientists, which is wonderful. I would like to take a couple of seconds for housekeeping items. At the very bottom of your screen, you're going to see a chat box and a Q&A box. Right now, most of you are introducing yourselves through the chat box. So if you have any question throughout the webinar, please ask a question. We are going to make sure that all questions are being answered either during the seminar or at the very end. We're going to address group questions at the very end. But if your questions are not being addressed for whatever reason, likely lack of time, please feel free to go back to the observing sections forum and ask your question there, and someone will actually get back to you and we can continue our conversation through our forums. Also, at the very bottom of your screen, there is a little microphone icon here. This is where you can control your sound. And there is a little setting here for your audio settings. If you have problems with your sound, we cannot fix it for you. This is something that you need to arrange from your own computer. So please be aware that this is a way of doing it. And without further ado, I'm gonna I'm going to stop talking and introduce Rich Roberts, who is one of the observing section leaders for the LPV observing section. Rich.
Hey. So I'm ready to take it away, huh?
All yours.
Well, good well, whatever time it is in your time zone. I was about to say afternoon, but that's only applicable to me. I appreciate you all joining us. And so what we have mapped out today a little bit is, for one, we're going to talk about why be an ABSO member, why study LPVs, and we're also going to, one question I get a lot is people ask me, like, hey, what do researchers or what scientists actually do with our data? So I reached out to two researchers who recently run ABSO campaigns and agreed to come on and talk about that. Also going to talk about a subject that's very dear to my heart, which is that of outreach. I do think that we have an obligation. We do a very good job of training our own observers or moving people who are already observers into becoming better observers, but also just reaching out to the next generation and building that next generation of astronomer, allowing people to understand that, hey, you can do this and you can be an astronomer or a scientist or an astronaut or whatever you want to be. People just sometimes don't understand that they can. And so I do a lot of outreach at schools, and we're going to talk about that a little bit more. And sometimes people don't understand. I was giving a presentation to one of an astronomy club, and the guy's like, yeah, I don't have a lot of money to invest in the type of equipment that I would need. And I was like, it's like, bro, man, you need $35 pair of binoculars. You can knock out probably a ton of stars in our binocular program. The guy had an 8-inch Dob. I was like, you could do 100 very useful targets with an 8-inch Dob. You don't need a lot of sophisticated equipment, especially if you're going to do LPVs. So moving on, one thing that
can I ask you to
when I started trying to,
can you change the slideshow, please?
Am I on slideshow?
At the very bottom of your screen. Sorry for interrupting, Rich. The icon that.
Better now?
Perfect. Thank you.
Okay. I was hitting F5 and it wasn't working, I guess. So when I started to try to think about the framework of what I wanted to talk about, I ended up going back to, those who are familiar with Simon Sinek, who's a marketing and leadership guy and an author. He developed this concept, what he calls the golden circle, and that you should always start all your messaging, all your product development, all your strategy with why. He's like, all organizations can tell you what they do, what they sell, what their product is, what their service is. Some organizations, maybe half, can tell you actually how they do it. When you say how, you're looking at what your differentiators are, how you go to market, that kind of thing. But very few organizations can actually tell you why they do it. And really the ones that can typically are the best, well-run and well-respected organizations. So everything that you should do, you should start with why, and then build out to how and ultimately to what. And so when I started doing this, I started looking at, why do I do this? Why am I an ABSO member? And really it all started, I've always just been fascinated with science and space specifically. And when I went to college, I studied astrophysics. Life took me in other directions, but I always wanted to recapture that connection to it. Well, eventually my wife surprised me one Christmas with a very nice telescope. And I started to take it out like most people do when it was novel and it was new. And I've quickly found myself getting bored just looking at Messier objects. And my scope weighs over 100 pounds. I'm not as young as I used to be. My back is not as strong as I used to be. I'm not just lugging all that equipment out to look at things. I needed a compelling event and to get me outside. Well, eventually one day I was reading about the women computers of the Harvard College Observatory. Fascinating story. And I came upon how when they started in the early 20th centuries doing the first photometric or studies of stars, and they realized that this concept of the variable star was not as rare as they thought it was. It is actually fairly common. And they didn't have the telescope bandwidth to really monitor. They could discover these new variables, but they didn't have the bandwidth to keep up with them and really develop their light curve. So they turned to the amateur community, and they were the ones that supported them. And I was like, well, that's fascinating. I want to do this. And I found out, hey, well, we're still doing it. And that same concept is still relevant, where we have the biggest, baddest telescopes out there. We can't use them to just monitor what a MIRA is doing, you know, over the course of months or years. Really, that's best suited for amateurs, and leave those great, real expensive telescopes to find new discoveries and let amateurs come up and really do the follow-up. And it's still happening today with missions like TESS and exoplanets and all that kind of good stuff. So I was like, wow, that gave me a compelling event, a reason to go out, to where not only was it I was like, I curse at the clouds because they're preventing me from going out. I want to be out there every day. And so 2 quotes that really spoke to me about this kind of model. And the first one is from Hertzsprung, where he talks about, hey, we have this debt to our ancestors. They went out and collected all this data, and we use it to understand our world, basically. And the only way that we can repay that is by doing that for our future ancestors. So when you think about some of these long-term light curves that we have that span a century now, that we can really monitor long-term changes in these stars, the fact that we can continue to add to that, that we need to continue to add to that, so that some future astronomer who will now have 200 or 300 years worth of data to really understand the long-term trends of what these stars are doing. And the other one comes from the founder of the AVSO, Tyler Alcott, who talks about using, you know, modest equipment of the amateur to put it to practical use. It's still relevant today. There's very few places in science, you know, you can do a lot of science history, and there were a lot of amateurs involvement who did stuff, but there's so little opportunity anymore because things get so much more sophisticated that amateurs can't really play a role. But this is still one place, and we've talked about it on this webinar series many times, where amateurs still can play a role and have a use in supporting science. And that speaks greatly to me. So why? It is part of being a legacy, something greater than yourself, something that's going to persist and be there for eternity that people can use. And that, you know, it also comes from a place of love. You know, I love talking to other astronomers who have similar views and passions than me. I've met a lot of great people in this role, and also doing something that, you know, really is important to me. And then you look at the next generation. That comes from going back to Hertzsprung. Hey, we're supplying data for future generations, but we also have a unique ability to train the next generation, not just train them, but also inspire them. I mean, there's nothing more I can think of that would be great that some high school kid saw what I'm doing and says, you know, I want to be a scientist. I want to be an astronomer or something like that, and then goes on that path. Another quote that really speaks to me for those who are geeks and like Star Trek, there was an episode where Data, he created another android like himself, and he made it a daughter, and he called her Law. And like most kids, she starts pelting him with all these questions, one of which is, why are we here? What is our purpose? And of course, he's a little taken back by that, because as he says, you know, the greatest philosophers of all time have been trying to answer that question. And how he puts these, like how I see it, is we're here to just take positive actions in our environment to make the world around us a slightly better place. And I was like, by being involved with something like the AVSO and doing some of it, by doing outreach, by collecting data, it's in a way gives me the ability, whether it be a small piece, I can slightly make the world a better place. And that speaks to me very internally, is a very powerful message. And when you look at why I do LPVs specifically, when I'm a visual observer primarily, I did to go the BART side, and I bought a used CCD the other day off of Cloudy Nights, and I'm learning quickly that I had no idea what I'm doing. But fortunately, there's plenty of people around I know I can reach out to. They will help me to go down that journey of being a CCD guy. But you know, these stars, the long period variables, are very well suited for visual observers because they have such large amplitudes. They move pretty slowly, so you don't have to have a real intense cadence. That's important to me. I live down in the coastal areas of Virginia. It's very hot, humid, and cloudy. So I can go 14 days or so without observing a particular star, and that's perfectly fine. You don't need much more than that. Also with visual observing, it doesn't take a lot of money. So this is also a good place to start if you don't have real expensive equipment. You start doing exoplanets or eclipsing binaries where you need really good tracking ability to do long time series. You gotta throw down some good amount of cash, but for visual, you don't. Also, what thing is interesting about LPVs are these are very aged stars, particularly the Miras and the semi-regulars, and we can see changes on human lifestyle timescales, which is very interesting to me. For example, this is T Ursa Minoris. This is what this star has done since I've been alive. I'm 40 years old. I was born in January 1980. I know some people on this call will think that makes me very old, and some people will think I'm very young, kind of a weird age. But this is what it's done since I've been alive. As you can see, this star is undergoing dramatic change. It's when I was born in January of 80, it had a 6.5 or so amplitude period, and and its period was like 330 days. Now it's more like 190 days, and its amplitude is very visibly dropped. So things are going on with this star. And it's because really their bread and butter, the Mira stars, the semi-regulars, these are very evolved stars. They're on the asymptotic giant branch. They're at the last end of their life, and things are happening very rapidly for stellar time frames, not necessarily human time frames. But we need to continue to watch these. There's a lot of them. People are like, oh, well, the Mira is not doing anything. I'm like, you never know when it's going to do something. Y Persei, for example, was being a very well-behaved, boring Mira until 1987, and all of a sudden it just changes behavior. We see a lot of these others that are slowly, gradually kind of changing now that we have enough data to look at them over a century or so, or multiple decades at least. So we need to continue to build that out. I know this is not applicable to all long period variables. We have a larger umbrella. We also own the RV Tau stars, which are kind of over here, and the supergiants like Betelgeuse, which are physically very different stars. But for Miras, this is applicable. So how do we do it as AVSO members? For one thing, it's the people are amazing. The members, I had no idea until I became a section leader how many people behind the scenes devote countless hours of their time, off time. These are all unpaid volunteers who develop all our programs, give observing tools, do coding for our tools. The staff is great. The AVSO actual pay staff is very small. They wear multiple hats. They work hard. They will do anything for you. And it's all because these members, the staff members, are all coming from a place of love and doing something, a little bigger and greater than themselves. And I think that is our why. Also to support all this, it comes from, even if you're a member not actively doing something behind the scenes, your dues are helping to support that. We have an endowment that we're paying down and also get grants. The other thing that we do that I don't have listed here is just professional amateur collaborations. We can help facilitate that. Professional astronomers do reach out and ask for certain things from us, our observers, and we go out and we do it. So that's some of our special sauce, as they like to put it. So what does all that bring to you is all the things, this is just examples of what we do. We write manuals to help train. We can provide mentors. I've been on both sides of this. When I joined the AVSO, I had no idea what I was doing. I was assigned a mentor. He got me up and running and going. And now I'm on the other side because I was a mentee. Now I'm a mentor, actually have my first mentee under my wing to try to get him going. We do choice courses, again, training, the observer tools. We have all those tools you think about, like VSTAR, VFOT, Variable Star Chart, the chart team. They're all unpaid volunteers who are out there doing things that support us. And then, of course, the Variable Star Index is a great resource with almost 1.5 million stars in it now. And Sebastian tirelessly makes sure that thing is up to date as we bring in more and more catalogs. There's a lot of stuff that the section or the organization does to provide to its members, all going back to from that place of love. In the section itself, to be specific to LPVs, I write articles to try to bring awareness, understanding of the physics behind these things. The circular is out there as a great resource to see what everybody else is observing to help guide you in your planning. The bulletin is there to do the same thing. Also, the LPV program, which was last updated like a couple years ago, that's really there to help herd the cats onto our well-developed long-term light curves. These are the stars that we really need you to continue to observe because they're scientifically interesting. And so we have all these tools out there to help guide you in picking what relevant targets are out there that have the most scientific benefit. You can get all these things from the section webpage. If you ever need to reach out to me, that contact button there works. Up at the top right, there's of the homepage, there's a thing that says observing section, go to LPV section. You can find the LPV program, the binocular program, all from this these file downloads. There's also Dr. Percy from the University of Toronto has a list of interesting stars that are exhibiting unusual behaviors. Those are great stars to observe. They're all found right here. Our target list is also updated. These are the stars that you should observe. And check out this other information down here. You can subscribe to our circular there, the bulletins there. The Myra variables with period changes is an interesting article written by Templeton several years ago, again, about stars that are exhibiting these behaviors that are doing changes that we can see on real time scales. So I will shut up now so we can go to the interesting speakers. And the first one, we're going to going back to that idea of research or outreach, because I'm a member of a local club. We do a lot of outreach. We go to schools all the time with our scopes to show kids the sky and let them know what they can do. It all came about one night. I was sitting there talking with my wife about the lack of diversity in our club. We go to meetings. She's the only Black person there. And we're kind of like, why is that? And she's only there because I'm there and because there's an ice cream shop she likes nearby. And so I can take her for ice cream. But the next day, my wife is a UVA grad, and there was in the UVA today an article about an astronomer at University of Virginia who had this organization called Dark Skies, Bright Kids that was doing outreach. I was like, oh, that's awesome. So I reached out. And so now we have a speaker from that organization who's going to talk more about it. And with that, I'm going to stop sharing and turn it over to Abby.
Hello, nice introduction. Thank you. Let me share my screen. Oops, I think I shared the wrong screen. There we go. All right. And are you seeing my presentation? Awesome. All right, so yeah, thank you. Hi, I'm Abby Wagner. I'm a rising third-year graduate student at the University of Virginia, and I'm one of the many volunteers that make Dark Skies, Bright Kids possible. So Dark Skies, Bright Kids, before I explain what exactly we do and what our goals are, oh no, I'm so sorry, I got a slide got deleted. Okay, well, before I explain exactly what Dark Skies, Bright Kids is about, I'd like to just take a second and ask everybody to think for one moment, what is a scientist? Picture a scientist. Like, for example, what are they wearing? What do they look like? What are they doing? And things like that. And so actually, Michael, your introduction was fantastic, because among those things that we think about when we think what makes somebody a scientist, or when we just picture and visualize a scientist, is actually determined by a lot of stereotypes that exist within STEM. So for example, I just Googled scientists and pulled up the images, and every picture that came up within like a reasonable amount of scrolling was somebody in what appears to be like a chemistry lab, mostly pipetting. We even get the mad scientist image pretty early on, where there's this crazy man with wild hair doing something crazy. And so these types of stereotypes are not just stereotypes, and they're actually something that is true and happening within STEM. So for example, within astronomy, 78% of all astronomers in the United States are male, and about 88% are white. And this is according to the sorry, I forgot what it's called. The United States demographics. So I can send that source out later if somebody is interested. But we as Dark Skies Bright Kids are a volunteer-run organization completely run by graduate students, and we seek to eliminate these stereotypes and biases, and specifically young children throughout the state of Virginia. So I actually have a video I'd like to share with everyone, because I think this video conveys our goals a lot more clearly and excitingly than I could in just a PowerPoint presentation.
I wish I had a program like this when I was in 4th or 5th grade to show me that science is super exciting and not just something that you go to class and that's it. Dark Skies Bright Kids is a primarily graduate student-run organization at the University of Virginia. We do a lot of outreach with elementary, early middle school age students in Charlottesville to bring astronomy into the classroom. All of our activities are meant as games or experiments.
Last week we did the impacts experiment. We have buckets filled with flour and they drop different marbles and golf balls for them to get a sense of like how different craters on the moon and Mars could have been formed.
It's more of an experiment and they have to try different things and see what works and what doesn't. And sometimes they come to the right answer and sometimes they don't. So it's teaching them that it's okay to not quite know and it's okay to guess.
Their sense of wonder helps them view the universe in a totally different way. They have no preconceived notions about how things should work or shouldn't work. They can ask crazy questions.
That's a lot of what astronomers do, is they ask these questions that seemed like they were a ridiculous question to begin with. You know, like, what do you mean the Earth's not the center of the solar system? Being able to get them into science and critical thinking like that is important at an early age.
The kids always have fun. That's our #1 priority. The age group that these kids are at start to think science isn't cool anymore. And what we're really trying to do is teach them that science is cool and this is for everyone. It's super interesting. You shouldn't be bored in your science classes.
It's really great to be able to provide these telescopes, provide the planetariums, provide all the different hands-on activities with the kids in our club and the community at large.
It's really important to us to reach as many kids as we absolutely can.
Learning with the kids and having them remind us that what we do is really cool. I think we get a lot more from it than we realize.
Cool. So thank you for watching that. But yeah, so Dark Skies Bright Kids, I think that video really summarizes our goals as an organization. And so now I'd just like to briefly go over like how do we achieve those goals within our organization. So the first thing that we do is we ask ourselves, what does it take to make a club or an event successful? And so we try to decide, in order to do that, we have to have a clear and limited goal choice. We have to have activity alignment with a journal. So we give the students like a journal that they can fill out as we do each individual activity. We include a high level of interactivity. And of course, all of our volunteers, we really emphasize positive attitude with the children, no matter what they say or guess, whether they're right or wrong in their scientific inquiry. And so in order to analyze how successful or not something is, the first thing we do is determine a learning goal. And we try to decide what message do we want the students to take away from that lesson. And by incorporating that, we design our assessments, which are the journal pages that we give the individual students. So for example, I have 2 little images up here, one with the solar system where they draw the Earth and Jupiter, the size of Earth and Jupiter based on the size of Neptune. An invisible light where we talk about infrared and X-rays and radio waves and things like that, and how light that we can't see is still light, but can be seen in different ways. We next implement these journals within clubs by seeing how the children react to them. And we have an assessment team that performs post-club evaluations to determine how successful or not we were at achieving that goal. And this becomes a cyclic process to ensure that that the children are benefiting as much as possible and actually learning the message that we want them to take home with them. And so now I'd just like to highlight some of the activities type of activities that we do. Our biggest type of activity is an after-school club. And so we actually go to different schools every semester for 10 weeks. We go every Friday for about two hours. And each club, each individual Friday is a different theme. So for example, our first club, we always focus on the night sky. We bring a blow-up planetarium and bring them in and point at what they will be able to see in the sky that night, and things like that. At this point in time, we have actually attended 10 schools for 22 different clubs. And we have launched 59 rockets, a number of which have been lost, but still very fun. We also, during the summer, do another club, but this one is set up a little different. It's a week-long, all-day club, and we travel actually outside of Charlottesville. So our after-school clubs are within Charlottesville, Virginia, which is where the University of Virginia is. But our summer clubs, we travel and stay at that location for a week and work with the kids all day. And do like 2 clubs a day, essentially. It's a week-long version of the 10-week clubs that we do after school. And I would just at this point, we have done 9 summer clubs, and we have launched 1 rocket at each one. Again, some of them have not been recovered, unfortunately. But I would like to just take 1 second to emphasize the summer of 2020, because obviously coronavirus made it impossible for us to have an in-person summer club, but we had decided pretty early on, or right around March or April, to decide to host an online summer club to open to any child. And so to do this, we actually made a lot of at-home activities, including assessments that they could fill out and write in, so we can also hopefully assess how successful or not they learned things, like we did in the in-person summer clubs. We mailed them a giant box full of activities that they could use. And we actually hosted our online summer club over Zoom and did the activities with them over Zoom. And this was an incredibly difficult effort. And I'd just like to highlight all of our volunteers that helped make this possible, because the children we had nothing but positive feedback. Parents and children were very excited to have done this. And I think it's just a very exciting thing to highlight, because even in the midst of coronavirus, outreach is still possible, and it was very successful. So I think other questions are like, how do we implement these science stereotypes, or how do we remove these science stereotypes at clubs? And one of the ways we do that is by including a featured scientist. So every individual topic that we cover, we also cover a featured scientist within that field. So for example, here are some of the scientists that we covered during our summer club this past year. And as you can see, we try to specifically target people in underserved or underrepresented groups within astronomy. So beyond our clubs, we also do one-off events, as we call them. So for example, Star Party is one of our biggest one-off events. I'd like to just thank the Albemarle Cider Works, which is a cidery not far, or within Charlottesville, or Albemarle County, which is near Charlottesville. And they let us come and set up a planetarium and telescopes and activities. And we host an all-night event for anyone in the public to come and view the sky and do a planet walk and all sorts of other things. Star Party is a lot of fun, so it's one of my favorite events. So in addition, Dark Skies, Bright Kids, we have a book called Snapshots of the Universe, and the book is actually written in English and Spanish. And so we try really hard to make all applications and everything else that we provide to children available in Spanish as well. We actually have money set aside to pay an undergraduate student to translate our activities and everything else into Spanish for Latino families that perhaps would be easier for them than the English version, English activities. So I think the last thing that I'd like to talk about is how do we achieve, or how do we measure how successful we are at removing these stereotypes, or how successful are we at trying to get these kids to realize maybe they could become scientists. And we do that using something called Draw a Scientist. And so before the kids actually start club, or when they apply for club, and on the last day of club, we ask them to draw a scientist. And we can compare what does their scientist look like from the application versus after the club. And so here I have some examples of different scientists that the children have drawn over the years. And some of these still are having chemicals and lab coats and things like that. But for example, this little boy drew himself. His scientist is him. And we are excited to see, like, we have started seeing underserved groups within astronomy are now popping up within our draw an astronomer or draw a scientist activities. We're seeing people looking through telescopes or giving a lecture or making a volcano and things, or working in collaboration, which is very exciting because we're trying to help the kids break away from these crazy man doing science in a laboratory stereotypes. And so I just like to highlight DSBK has been running for for 10 years now, and it has been a completely volunteer-run organization, almost exclusively run by graduate students. We have had a very minimal amount of help from faculty, and so that's a huge accomplishment that we have been able to survive and thrive for this long. We have hosted over 344 events, and we've reached over 22,000 kids. And just recently, our assessment group had a paper published on analyzing the Draw a Scientist test. And so if you're interested, that paper can be found. I don't know if it's publicly available, but yeah. And I'd just also like to emphasize real quick, there is an event happening on August 10th called Astronomy on Tap, which is not directly related to DSBK, but a lot of us that volunteer with DSBK are also involved with Astronomy on Tap. And it's open to anybody, and we have a few speakers talking about like citizen science, and so I thought it might be interesting to like this group. But yeah. So thanks. I would like to just emphasize one more time, DSBK is completely volunteer run, and we are very dependent on our sponsors and donators. So if you're interested in donating to DSBK to make sure that this organization can continue to thrive, I recommend checking out our website. Thanks.
I appreciate it so much. Abby, I really enjoy this thing you're saying, especially the draw of the scientist. And two of the examples when you showed up pictures of scientists, definitely Andy John Cannon and Maria Mitchell are very pertinent to the history of variable stars, because they made a lot of discoveries that really variable star related. So that, yeah, they belong to us too. So I thank you for coming. I enjoyed the talk and great work, man. We really appreciate it. And hopefully, like I say, I'm down in Hampton Roads, so I might be reaching out, see if we can bring some of that collaboration down into my part of Virginia.
Yeah, absolutely. Thanks.
And so next up, we have Michael Stroh from Northwestern University, who recently ran a campaign on masers. So I look forward to you. And turn it over to you, Michael.
Michael, you're muted.
Yeah, sorry, just trying to figure out the sharing between my screens.
while Michael is setting his screen, I would like to remind everyone, if you guys have any questions, if there are any questions from our audience, please put it in the Q&A box that is at the very bottom of your screen, so that they will be addressed by our panelists. Thank you. Go ahead, Mark.
Okay, can you see it now?
Yep, we're
Okay.
good.
So I'm, actually let me move, I have something else on here. Okay. Okay, so yes, I'm a postdoc at Northwestern University, just outside of Chicago. And I've been using running a Maser / AVSO campaign that I'll be talking about today. So my talk is split into 3 parts. First, I'm just going to introduce masers and circumstellar masers because they're a bit of a niche field. I wouldn't be surprised if very few people have heard of them. Then I'm going to move on to the larger big survey of the circumstellar masers and then how that helped lead to this and motivated the work with AVSO. So maser is an acronym. It's similar to lasers. It's just different wavelengths. Lasers you see in the optical, masers you see in the radio. So this is an energy level diagram for a molecule, little cartoon. So you could imagine a molecule starts in some low energy state that's depends on whatever the temperature of the gas is. And then you can have what's called a pump. It can either be collisions in the gas or it can be the radiation that hits it. But either of them can inject energy into the molecule, move it to a higher state. Then the molecule can de-excite. It can be a series of de-excitations until it becomes stuck at a metastable state. And for some reason, it wants to move down, but it just can't. But you can stimulate emission by having a photon with just the right energy equal to this energy level gap. And if it hits the molecule, it can stimulate emission. So instead of you had 1 photon to begin with, you have 2 photons. So this is an exponential process. So you get very bright lines. These are different than thermal lines that you're probably used to in spectroscopy. And so you can imagine if you have a huge cloud, a dense cloud, this will happen over and over. Each photon will interact more and more, and then you end up with this very bright light. And if you don't understand this, that's okay. It's not gonna make or break. Hopefully you're understanding the rest of this talk. So I'm gonna focus on AGB stars in this talk, whereas you get most of the circumstellar masers. So these are late type stars. They're very bright in the infrared. And you can potentially have 3 different types of maser emission. So if you're an observer here, looking at this star, very far out, like maybe 1,000 AU from the star, you can potentially have OH maser emission if it's a very dense environment. You can also have water masers closer in. And then at the very closest, usually just a few AU from the star, you can have SIO maser emission. And these are AGB stars, which means they have radii of about an AU. So the SIO maser emission is relatively close to the star. And this is the spectra that the observer would see. So if they were observing the cloud, or observing the star and the clouds around it, they would potentially see some blue shifted OH maser emission, some red shifted maser emission, and then the velocity of the star would be somewhere in the middle. Water is complicated spectrum, but SIO maser emission is a really good probe of the stellar velocity. And in particular, I'm going to focus on Meyer variables for the rest of this talk, as well as a further subset, because they are the best places to find SIO maser emission. So when you look at, if you look at a star with very high resolution radio observations, the SIO maser emission will be in a circular ring around the star. So the star would be here, you have this maser emission around it. So that's why you don't have this blue shifting or red shifting. You're seeing this ring that's just basically at the same distance from the star as you. It's not moving towards you or away. So now I'm going to move on to the larger survey that inspired this rest of this work. So the BADE survey's primary goal is to improve our models of the dynamics and structure of the inner galaxy. And because these are masers, that means we can observe them in the radio. Also, since they're masers, they're bright, so we don't need that much time on them. So we've, through some color selections, we've been able to select 28,000 stars. These are likely all Miras throughout the galactic plane that we can observe for the study. So here at the bottom, here's the galactic latitude and galactic longitude. So this is you just looking right along the disk of the Milky Way. And this is our target selection, all the targets for our campaign. And also, since these are radio observations, that means we don't suffer from the confusion and dust obscuration that you have with the infrared or optical campaigns. So hopefully we can probe all the way through the Milky Way. And our main workhorse for this survey is the VLA, which I'll talk about shortly. It's in the Northern Hemisphere though, and that means that there's a significant fraction of the Milky Way that we can't see. And for that, we then supplement in this region with ALMA observations. And ALMA is another radio interferometer that's in the Southern Hemisphere. So another way to look at the coverage, if you were looking down at the Milky Way, the sun would be right here, and everything in red is what's covered by the VLA, and everything in blue is what's covered by ALMA. So hopefully we have a really great coverage of the whole region. So some images in perspective. So this is what the VLA looks like and one of its compact configurations. So these are all 25-meter diameter dishes. There are 27 of them operating at any time. And it's an interferometer, so it combines the signals from all these dishes to create a final spectra or image, depending on what you're using. It's in New Mexico, and in particular, we look at this SIO mission that's at 43 gigahertz. ALMA, it's in the Southern Hemisphere, slightly smaller dishes, but a lot more dishes. It's in very high altitude mountains in Chile, and we look at a slightly different set of SIO transitions. That's just because the two instruments operate at different frequencies. So VLA is our main workhorse though, and that's also what we're gonna we use for our AVSO campaign as well. So in the end, we get a bunch of spectra that look like this top figure. This is actually two panels. So this is the frequency along the bottom, and then this top panel is the amplitude in units of Jansky, which radio astronomers use. This bottom panel is zoomed in so you can see the weaker lines a bit clearly. So there's this little bump here, but you can see it much better in the zoomed in figure. So there are, the main lines that we usually detect are like this V equals 1 line, this V equals 2, and this V equals 3 line. These are the main ones of importance. And then the others are just bonus if we find them. But anytime we find more than one line, then we're more confident in the velocities that we get. And at the bottom, I have another picture of the galactic latitude and longitude distribution of our sources. The entire VLA sample has been observed, and one of my colleagues is trying to finish up the last couple thousand sources analyzed so she can get her PhD. And ALMA, we're slowly working on that. We just need ALMA to give us more time so we can finish it off. So the key deliverable for the survey is the velocities. So we get a line of sight velocities of all these stars, and then we can look at the dynamics of the galaxy. However, I'm more interested in what is causing the maser emission. There are a bunch of other molecules as well that also maze in certain special conditions, and a lot of them are much more understood. However, SIO is a bit of an outlier. There's still a debate on whether it's collisions or it's radiation that's doing it. And the reason is because these are chaotic environments right outside of these long period variables. These are evolved stars that are losing mass, so it's easy to have collisions as all this mass is losing. And it could also be radiation because most of these are variable stars. Most are Miras, which are highly variable. That's a few magnitudes in difference that they're moving. So there's debate on this, and there are groups modeling both of these, hoping that one will be the answer. So what I'm trying to do is go back to our spectra, understand what the what we can see between the relationships of the lines and how we can then test the models to understand what causes the SIO maser emission. If we understand fundamentally what causes the SIO maser, then we can turn it around and say, well, I see these measurements, so therefore the star is this and the density around it is this. So maybe if we understand this, maybe we can understand parameters such as the temperature, the density, the metallicity. Maybe we can also have some constraints on the mass and the age of the star. So that's my particular interest. And one of the key reasons for that some groups believe that radiated pumping is significant is because those first two primary lines, the V=1 and 2 lines, those seem to be correlated with the infrared light curves. So people think maybe it's the infrared that's causing this pumping. So I'm going to start on this figure here, which is pretty complicated. It's okay. You don't have to understand it fully. So this is basically, you can think of as the luminosity of the line along the y-axis, and this would be the density along the x-axis. So as the density increases, that means that the line has to be closer to the star. So that means if we look at these pairs of blue lines versus green lines versus red lines, the blue lines seem to be in the less dense environments compared to the other two, so they should be further out. And the red lines should be the closest ones in to the star because that's where they're going to be most dense. So this is a very simple radiative model. However, in high resolution radio images, this group, Demir 2014, they showed that actually all three of these lines, in particular these solid ones, they tend to be in the same vicinity. Maybe they're not right on top of each other, but the circles indicate the same distance. So the theoretician in that group, she really went to town on her models, and she added more oxygen-bearing molecules to her models and found out that then the whole energy levels have to change in the models. And water in particular is very important, it turns out. And by adding that in particular, you can then, in a region where these solid lines, the red, the green, and the blue all peak in the same density neighborhood. So this is more reason that maybe these radiated models are important. And the reason you want oxygen-bearing molecules is because if you have SIO, you're probably in an oxygen-rich environment. If you're in a carbon-rich environment, then the oxygen is probably bound to the carbon. So one thing we did is we were interested in how bright the 43 gigahertz lines were compared to the 86 gigahertz lines. We wanted to understand how complete our sampling was. You know, if one line is much brighter than the other, then when we combine our two samples from our two instruments, ALMA and the VLA, we'll have to do some bias adjustments. So we looked at that, but what I found was particularly interesting is if we, so this is a distribution comparing the brightness of the 43 gigahertz V=1 line versus the brightness of the 86 gigahertz version of it. And when we do have that 43 gigahertz V=3 line detected in the same source, we have this outline distribution. And on average, the two lines are about of equal brightness. However, when we do detect this V=3 line, the distribution shifts. And in that case, the 43 gigahertz line is significantly brighter than the 86 gigahertz lines. So if any bias we find between our samples is going to be sources that have this line. And what was also interesting is we found another difference in the distributions when we compared the V=1 and 2 lines, both to 43 gigahertz. In this case, it wasn't a shift. Here, when we look at the brightness of the V=2 line compared to the brightness of the V=1 line, we have this pretty wide distribution that's outlined. However, when this V=3 line is detected, these two lines are much more tightly coupled and correlated. So this was nice because if they were both like shifted, that might mean that maybe our data analysis had issues or there was something else happening. But since these are two different one's a narrowing and one's a shift. That seems to indicate that there's something really interesting happening and it's real. And so that's when I came across that model that I showed earlier. So I'm deconstructing it a little bit to just the important parts. So if we find this v=3 line according to that model from Demir 2014, it's probably going to be in the brighter area, so brighter density range. And in that region, the density space, we are in a region where the v=1 lines are brighter at 43 gigahertz versus their 86 gigahertz counterparts. So that seems to match what we're seeing. And if we add in this v=2 line and compare that in the same density regime, we see that, yeah, that's actually a region where these two lines are highly coupled as well. So we really wanted to follow this model further and test it to understand how we can use the SIO maser lines to test the model and also figure out what we can learn about the circumstellar environment by using both the individual line strengths, how bright they are as individuals, or how they are relative to each other. So a couple other things is in the literature, there have been some people who have noted that they only seem to detect this line here, the red one, the v=3 line, when the source is at its brightest in the infrared. So it seems to be tied to variability. And there have been other studies from the 80s that showed actually that both of these two lines are also tied to the light curves. Now now these are all correlated probably to the infrared light curves, but I should note that the infrared light curves tend to lag the optical by about 10 to 20%. But they're still correlated, those two light curves. So even if we can't get infrared light curves, optical light curves are extremely useful for probing this and figuring out if this is something to do with stellar phase or if some sources are just inherently different. For instance, is this v=3 line, as some have proposed, only found during the infrared bright phase? Is this line found in all MIRAs? So all MIRAs then cover some density regime? Or are there some sources maybe that are more dense and in their circumstellar environment, and maybe you see this more often? So these are some of the questions we wanted to probe. And so to do that, we needed to utilize AVSO. So to do that, I took the 28,000 sources in our full sample list, correlated that, or actually I think someone from the VSX actually helped correlate that for me, to figure out which ones were known variables, which ones had periods, things like that. And then that we sub-selected on that sources that had a history of AVSO observations, because we wanted to actually go after stars that we knew would be fruitful, or at least for the most part. I think we ended up adding in a couple that bit of Hail Marys, but it worked out in the end. So we did that, and then we asked some further questions. What were their periods? We wanted at least the majority of these have periods that we could cover once or twice in a 2-year period. We wanted to make sure that they were all observable by the VLA, so Northern Hemisphere targets, so that we could use the VLA as our main observing instrument. We wanted to make sure that we had SIO detected in the original BADE survey, so that we would hopefully be able to follow it and not just hope that maybe we saw it at the bottom and maybe it'll come up. And we also, because we're unsure what's going on with this v=3 line, we chose half of our sources that had v=3 in the initial observations and half that did not have v=3 in the initial observations. And in the end, we ended up with 20 stars. The majority are MIRAs. One is a semi-regular. And all semi-regular means is it just doesn't have, may not have quite the brightness variations, or it may not be as regular, but it's still probably closely related to the MIRAs. One supergiant, which could actually mean that's a whole different type of stellar evolution, something that started out more massive on the main sequence. And one of the Myras is actually also an OHIR star. And the OHIR stars tend to be the more, the stars that have thicker circumstellar envelopes and have that OH maser emission. So Myras usually don't have that OH emission, but they'll just have the SIO, whereas OHIRs, they're having more mass loss and thicker circumstellar conditions. So we have a few that we can also compare against the Myras. So altogether, we end up with 2 observing campaigns happening in concert. We had the VLA campaign that started in November 2018, and it'll end in a couple months. We try to go for observation of every source every 3 weeks. In total, it takes an hour and a half. And so far, we have about 30 epochs in total. So we'll complete this in the next couple months, and it'll keep me busy for the rest of the year. AVSO has just been incredible. I can't believe how many observations have been submitted since our observation started in August 2018. And we tried to start observation, we requested observations before the November 2018 because we knew we'd have to shift the light curves by 10 to 20%. And also just having maybe a little bit more coverage in the light curves will help us interpret what's going on with the radio. But tremendous effort by AVIA, so I'm really amazed, and so are my collaborators. So I'm a bit behind on the radio analysis, so I'm gonna show just some very initial figures from about a year ago when I defended my thesis, and this was a chapter in my thesis. So at the very top, we have observations from AVSO in I, and this is V. There's a B data point, I think, here. We also have some SWIFT data, which is an observatory in space. I have here. And a couple months before I defended my thesis, I realized that the Zwicky Transient Facility, which is a state-of-the-art ground-based facility, is taking all sky observations and releasing some of that data. So this is a state-of-the-art light curve. But you notice it ends here, and that's because it saturates. They can't observe above 12th magnitude. However, this is something that AVSO is able to sample for us a lot more effectively in these brighter regimes near the peaks than ZTF can. So this is really nice that we get this and that we plan on using AVSO from the beginning instead of hoping that maybe ZTF would work for us. So that's great. And then from the radio side, this is nice because we do see from the initial observations that these 2 lines, this is the V equals 1 and 2 lines, they are starting to couple a little bit slightly after the peak. So this would be where we would think it would, near the infrared peak. Here's another quick example. This is the OHIR star, which has a denser environment because of this OH maser emission. So here's the AVSO light curve, and then 2 other bands as well. V is really nice. But we see something very interesting. So we see this coupling, which would make sense if we're coming off of the peak. However, we see that the V equals 2 line is actually brighter than the V equals 1 line. And this is really unexpected. But it could mean that we are not just in this regime, but we are in this higher regime, higher density regime, where this V equals 2 line in green here is brighter than the V equals 1. So this has me really excited. I'm looking forward to looking at the source some more. So I just want to show quickly the status of the light curves and some of the bands. So here are 10 of the sources. They look really, really well sampled. Here's the other 10. So this flat one is the supergiant, so that's why it doesn't have the same variability. It's not a Myra. But this is just amazing data that we have. I want to say special thank you, while I have time, to some of the people who helped with some of the VSX and AVSO cross-matching at the beginning of the survey to help me get it started and plan it. Also some people here who reached out to me via email and helped me understand some things, what worked and what didn't for the observers. Richard for inviting me here to talk today. people who also just were responding to each other on the forums to make this a very successful observing program. And probably thanks most of all to Elizabeth, who just has been extremely helpful getting the alerts out to the community on what I was requesting. And of course, the most important people here are a bunch of the observers who have taken just an extremely large amount of data for me. So I want to say thank you. That's it.
Thanks, Mike. I appreciate it. I mean, it's always great to hear that your data is being used. You'll see I was on there. I took on a couple of these stars, you know, because it is important, as I mentioned earlier, to make sure that we have these developed light curves that span multiple decades. But it's more exciting when a researcher actually says, I'm looking at these stars now and I need data now. I know when this campaign was running, I was always excited whenever like Cepheus and Cygnus, some of these stars were within my observing limits and well positioned, so I could go out and make observations on them.
Yeah, I heard that I got some feedback from some people in the community that there was not enough long period variable surveys. So they were really happy to see one that was going and that I was using the data. So I'm trying to keep in mind as I try to finish this project off is think of, okay, what can we do next? What's the next thing we can do that AAVSO is really the best to support?
Awesome. That sounds good. I look forward to it. And speaking of that, we'll transition to another star I like to observe with our Aquarii and other symbiotics. Symbiotics are quite LPVs, but they're very interesting stars. I like them too. And so with that, Margarita, we'll let you take it off.
Can I share the screen?
Yes, ma'am. Go for it.
All right.
There we go.
There we are. So, first, greetings to everyone. Good afternoon, good evening, good morning, wherever you are. I'm amazed by the wide outreach here and so glad to be with you all virtually for now. Thank you for inviting me to be on the panel. So the title is a little bit focused on our query, but mentioning other symbiotics. But the subtitle is Sub-arc second resolution view of wind accreting symbiotic binaries. And a very important part of it, the AAVSO-led observing campaigns, including photometry and spectroscopy, that have been a key for the observations that I will describe to be successful and get amazing results. So thank you, all observers. Thank you, Stella headquarters, all the members headquarters, the ARAS group, all people who have been doing diligent, beautiful work so we can do this fantastically exciting research. I am at the Center for Astrophysics, the new name, Harvard and Smithsonian, so CFA, and I have a number of collaborators from CFA and from the Hubble Space Telescope, BLA, and from elsewhere. I will be using some of the graphics that are from different press releases or work by, for example, 3D modeling from the University of Minnesota group and so on. So I will just use to illustrate a little bit better of what is going on. So first, symbiotics, just a first overview will be a little bit what are the symbiotics and what are the questions that we are focusing on. And then importance of sub-arc second resolution observations of few nearby symbiotics, the role of the AAVSO-led observing campaigns, and then show some results for our query and a couple of other symbiotics. So symbiotic systems interacting binaries consisting of an evolved red giant Myra type star. You see the red star there in the background, which is losing mass, and the mass is accreted on a compact accretor, which can be white dwarf, even neutron star, or main sequence star. Accretion disk, we think, is formed around the accretor, and then there is overflow of matter that is ejected from the system, and in systems, in some of them, via jets. These systems are quite an important subset of interacting binaries for a number of reasons, but they have been invoked as progenitors of planetary nebula, asymmetric ones, and also supernova type 1a. Supernova type 1a, as you know, are key objects in determining the spatial scale of the universe and the expansion of the universe, including the acceleration. So knowing the progenitors and how things work is really very, very important. And I'll tell you why. So here it is, you have a red giant on the lower part of this panel, and accreting white dwarf, a compact source on the top. The red giant is using Myra, is losing a significant amount of mass through a powerful wind. A fraction of that wind is accreted by the compact source. The Bondi-Hoyle theory proposes it's about 1%, you know, as it's symmetrically thrown into space, the wind. However, we have observational evidence that even when the companion is not in the periastron, the accretor, the matter flows through a focused wind accretion. Why is it important? If you can dump enough material on a more massive white dwarf, 1.3, 1.2 solar masses, you can dump and keep it there. With the time, you may have enough of a mass for the system to explode as a supernova type 1a, and so on. So knowing the properties of the mass loss and the accretion properties of the system is key. And that's our study. And those parts are not so well understood. So accretion is actually one of the most powerful energy generating mechanisms in the universe. It works for young stellar objects, but it works for AGN, galaxies with supermassive black holes, interacting binaries, and so on. However, for many of them, you cannot resolve the region where the major things are happening on a scale. For example, you take the binary stars comparable to the orbital separation of the components. So nearby symbiotic systems within 1 kiloparsec distance, about 1 kiloparsec distance, are unique laboratories for studying accretion processes, especially wind accretion and associated phenomena, which include outbursts, jets. So by resolving these stars, the components and the region surrounding them, we can study this system at spatial scales comparable to the orbital separation. For this, we need multivalent observations. I'd say from X-ray to radio, but gamma rays are not out of it, at least one object had shown. And we need maximum subarc second resolution. Of course, I'll show my bias here, Chandra, HST, and VLA, but they are ground-based observations, of course, with VLTI, ALMA, and so on. And VLA. Plus, key to this is using the information on the variability of these systems. These are long period variables. And you cannot say, well, 10 years ago, you know, a year ago, a few months ago, this is what the system was doing. And I am going to go and plan an HST observation or Chandra and so on, or VLA, and just get my data. So therefore, AAVS observations and spectroscopic observations, including the Aras group, François Tessier and others, are key to successful study of these objects. We need a very good knowledge of the telescope instrumental point spread function, telescope and instrumental point spread function, because by using the convolution techniques, we can reach resolution which is less than 1 arcsecond and less than 1/10 of an arcsecond, while with the, for example, with HST to 0.02 arcseconds. Using the ground-based observations, the light curves, light curves, our spectroscopy and our spectroscopy, through the campaigns, we can identify the pulsation phase of the Myra or the giant component, which is usually dominating the light curve, but also we can identify epochs where there is increased activity. Something is happening in this particular system. So there is our dear friend Myra AB, one of our special friends. The light curve shown here is dominated by Myra A, Myra, the prototype of Myra type variables, with 7 magnitudes amplitude variations. For most of our observations that I will tell you about, we'd like to observe at the minimum, and I'll tell you why. So a few years ago, we resolved Myra, we observed Myra in optical, ultraviolet, and X-rays. And you show on the left the Chandra image resolving the component. Myra A is to the right, Myra B is to the left, and same with the Hubble Space Telescope. At that time, unexpectedly, the Myra A went in some kind of outburst. You know, that's another thing that we'd like to learn about these Myra and stars and giant stars. Why do they go in outbursts? And when you have a companion, the companion serves as a probe because it accretes the material, and there is more material, there is more flow, and so on, and more material held in the accretion disk or ejected into a jet. So in these images, you see also the bridge between the two components that has never been seen before. This is half an arcsecond separation between components on the sky, about 80 astronomical units, or twice the distance to Pluto, distance between components. They should be detached. There shouldn't be flow of the matter. So this initiated the idea of focused wind accretion, where you can focus the mass lost by the giant, by the evolved star, the LPV, focus and bring more material for the white dwarf to accrete. Now, why is it so important? I said at the minimum. Imagine if this was done at the brighter phase of Myra. Well, look at the HST observations. These are the convolved images. But in HST observations, it would have been dominated by the point spread function. It would have obliterated any possibility for the convolution. So, but for X-ray, we have a UV leak if this red star, we have a leak if it's too bright. So I would have had a doubt whether these X-rays coming from the Myra star, which have never been detected, they are rare, almost people thought impossible that the Myra have X-ray, the Myra types has X-ray. I would have thought, oh, that's because we have a very bright star. Well, it's not the case. These X-rays are real, and there are other sources that have been detected since. We come to our query. This is a beautiful image. It comes from the Chandra press release, but it's ground-based optical observations combined in red, combined with X-ray observations taken over years. You see there have been explosions and outbursts over many years in this system, and this is a large scale, like 30 minutes, what you see that ringy structure there. The blue is the jet. Our query, the system is this little red box. I hope you can see it in the middle. But what you see in blue is the powerful jet emanating from this little binary consisting of a Myra star, a white dwarf about 0.6 solar masses, we think, and a separation of about 15, 20 astronomical units. Our query also is dominated by the light curve of the Mira star. And if you see in the late 70s, they detected, Leon Wilson is very much aware of it, they detected absorption in the light curve and changes in the light curve that are very likely associated with a periastron passage of the companion, mass ejection, and formation of a cloud that they stayed there and eclipsed the whole system for a while. Now, the most kind of advanced orbit by Mikolaevsky and so on predicted that the next periastron will be in 2022, 23. So Leanne and George Wallerstein and other people, including myself, my group, we kind of started thinking, let's see, observe. There were calls for AVSO to start following it early. And so we are getting some data, 2019. In June, I was on vacation in Europe, came back in the beginning of July, and I check my beloved stars, my symbiotics and others, see what they're doing. This is what I saw, the third cycle there, not the last one, when I open when I use the AVSO access to the light curve. Look at that. The object should have gone through the maximum in mid-June, but the peak there, a dud in visible, a dud in B. I mean, what happened? So I called Elizabeth. I said, hey, Elizabeth, what's going on? So Elizabeth went and checked. No, she said, these are real data. Wow, they were expecting it, a couple years later, 3 years later. So we waited a little bit, a month or so, just to see whether it comes back or what it's doing. Starting somewhere from August, started writing proposals. Target of opportunity, discretionary time. So from September to February, September 2019 to February 2020, we got VLA observation, we got SWIFT, we got HST observations, we got Chandra observations. And it's just magnificent. It is so magnificent that I still feel like being a kid in the candy store. We would not have known if the AVSO did not detect it. The spectroscopist, amateur spectroscopist, the Harris group and others jumped at it, George Wallerstein, and you have spectra at the same time and photometry. And just ALMA happened to observe around that time. So just beautiful. Now the system went from maximum again, now in July, and look at that, still very much absorbed. So still something is absorbing the Mira star, but seems the companion as well. And the minimum is very, very low. And the observations that we got them with close to the minimum. So the image that I will show was not overwhelmed in the center, but the point spec function of the Hubble Space Telescope, where we got dozens of filters and so on. So shown here in green is oxygen 2 Hubble Space Telescope, WFC3 observation, showing the jet to the northeast and the counter jet to the southwest. The red is the soft X-ray emission from Chandra. These are all the convolved images because trying to reach the maximum resolution. Look the scale. The little circle is 0.4 arc seconds. Look what's happening within 1 arc second. The blue is the hard emission from 2 to 7 kiloelectron-volt from Chandra. The next image will just show very similar thing, but I've just put the ALMA observations from 2017, not the newest ones, and emphasize the soft X-ray emission. You see how they are interwoven. VLA is also there and very similar to what we get from the Hubble, different wavelengths. So it's very exciting. The preliminary results are being written now in the paper. I hope we have it soon. And then a lot of work is being done for analysis of all these multivalent observations, including SWIFT. And we are very excited to welcome to the group postdoc Caroline Huang, starting from September. She's going to have lots of fun. So I have, do you have 5 more minutes? I'm on 20 minutes now, not less than 20.
Yes, you have 5 more minutes needed.
So another beauty, CH Cygni. CH Cygni, this is a 50 years chunk of the light curve of the CH Cygni. CH Cygni has a giant donor star and a white dwarf accreting. Again, not very massive white dwarf, but in the 80s, 70s, late 70s, 80s, we see a sudden drop in, this is about 1/3 of the light curve in the light curve absorption. Janet Mattei and collaborators suspected there is a jet, and there was a radio that detected a jet at that time. Since we have been looking for these drops, sudden drop, dimming in the light curve, and then following up with a campaign, we are looking for this with the AAVSO campaign. We have been looking for these drops and trying to identify formation of new jets, which we have detected and have as an example of the CH Chandra HST and Vela observations from 2008, and we have more recent ones. The blue square in the middle, that's where the binary is. The counterjet, look at it, how it's extended. It's 4 arc seconds away to the southwest. The green is HST, the red is Chandra, the blue is Vela, and the counterjet is to the northeast. Velocities of 1,000 kilometers per second. Another, now this one, the spectrum that I'm showing you just very quickly is from the International Ultraviolet Explorer from 1990. So that is a few years ago, but it's still very, very similar. It shows very deep and wide absorptions. I work also on AGN and active galactic nuclei and CFET galaxies. And I didn't know that this is a symbiotic. I would have thought that this is actually a quasar or an AGN star with broad absorption line region. The velocity that they measured in a recent paper, Lucy et al., of the order of 6,000 kilometers per second of the jet that has been ejected, and it's kind of, they propose, is pointing to us, like looking down the barrel. AAVSO has been observing it, and including recently, when you see an increase in the observations to the last part of the light curve, that is when we call our dear friends observers, AAVSO and ARAS and other observers, to focus on this star, a campaign to observe this object, because we got some gorgeous observations in X-ray, well, with Chandra, with the XMM, but also especially with the HST, and we are working on these observations. So they are speaking about looking morphologically like what we see in AGN and quasars. There are microquasars where you have the accretor is a black hole, but people have invoked the name nanoquasars for these symbiotic systems. The scales, the magnitude is different. However, the morphology and some of the accretion processes are very similar. So therefore, the laboratory is to study these beautiful, fascinating systems and then understand systems that are much further away, more massive, of different type of beast. So quick summary and conclusion, multi-wavelength high angular resolution studies of individual components of interacting binary systems is very important in order to be able to model the accretion processes, especially wind accretion processes, not just in symbiotic systems, but in other systems in the universe. Even in detached binaries, which the symbiotic systems are considered because there is no Roche lobe overflow during most of the orbital motion. An evolved giant component is sending wind that is focused and accreted by the companion, and the accreted amount shown by the 3 hydrodynamic models that we have developed and others show an order of magnitude higher amount accreted, which is very important when we talk about the possibility of supernova type Ia or asymmetric planetary nebula. So following it and understanding the mass loss characteristic of both components is key, and following it in time because they're long period variables. So key to our study of the dynamic evolution of symbiotics, which are long period variables that includes the Myra and the giant and the accreting companion, is long-term photometric spectroscopic monitoring and observing companion. This will help us identify epochs of increased activity associated with outbursts in jets. I list several of the symbiotics on which we are working, including our query, and especially activity related to periastron passage of the accretor, detecting the early periastron passage, the effects of it, like it is the case in our query. So I thank again very, very much the observers and everybody who had helped this research to be possible, and very grateful for the campaigns. So this is my presentation.
Awesome. Thank you so much, Margarita. I enjoy observing symbiotics too, because they're just so kind of quirky a little bit. They're interesting stars. And Leanne had a couple of stories that she wanted to share about our aquarii, because she's spent a lot of time studying the stars as well. So take it away, Leanne.
So I thought it might be fun to just mention that a little bit of the history that Margarita alluded to. So back in close to 1980, 79, 80, or 81, I was visiting AAVSO headquarters, and we were working on a project to look at Myras that occasionally behaved strangely. The amplitude changed, the periods perhaps changed, sometimes it was hard to tell. And one of the stars we were looking at was our aquarii. And we were looking at the light curve, and we plotted up the maxima and minima. And here you can see from the paper from 1981 that the maximum came down and the minimum came up in 1933, 34. And this was an event of some sort lasting about 6 years. And then we noticed that we had just missed one. And this one was with a dip in 1977, 78. And so we had just missed this event. And from the infrared behavior, we realized, so this is the distribution of energy from the star. You can see it peaks up in the infrared, so that's where most of the power is coming out. In order to push that peak down, you need something pretty amazing. And if it's the star changing its behavior all by itself, you expect big changes in the period and maybe the color and other things, which we didn't see. So it had to be something getting in the way of the star, getting in the way of the Myra, and it had to be something that blocks 60, 80% of the light from the star to push the infrared light curve down. So we predicted that centered around 2022 and lasting for about 6 years, there would be another one of these events, this eclipsing kind of event. I remember thinking at the time, oh my God, I'm going to be so old when that happens. I might even be retired, which I now have been for 6 years. So then in the recent time, we noticed that there was an unusually low minimum, that most of the minima are around 11, and this minimum went close to 12. And this was a little early. It was earlier than I expected anything to happen from this star, but I got in touch with the AVSO again and said, maybe we should start encouraging observers because we might be getting it, we might have the period wrong, we might be wrong in some way. And that was fortunate because now we have some really good infrared observations leading up to the current event. And the current event then becomes more obvious in the last couple of cycles, just as Margarita showed. So that, when it finally started to go down and went way down and came up to a low maximum, it was like, I've been waiting for this for a little while, 40 plus years. The other fun thing I wanted to show was just that in the last minimum that we had, there were some interesting things happening down here that are probably associated with the companion and the accretion and the flow, and time scales are always so useful in pinning down the physics. So in the visual light curve and in the, I think this is the blue light curve down here, we had these wiggles. And so that's going to provide some really useful constraints on what's going on. And I also want to point out that we have this 2.5 magnitude decrease in brightness is actually not just the visual and the UBV, but also the red and infrared, the RNI colors are being suppressed just as they were last time. So something pretty opaque is blocking out one heck of a big star. And I'm with Margarita. I think we're probably looking at a focused wind flow. And this is a chance to, in various ways, resolve what's going on, because our time dependence may also give us a kind of resolution of what's happening. So this is really exciting. And I've been waiting a long time for that one. Okay, I'm done.
Wonderful. Thank you, Leanne. If you could stop sharing your screen so I can actually share mine again.
I'm gonna find that for a second. Just gotta,
sure. It's wonderful to actually make a prediction of something that you're looking forward to seeing for decades, something that is so big in terms of scales and time scales, and actually for it to happen within your lifetimes. It must be very satisfying. I would like to, was that?
George Wallerstein's also been involved with this, as you mentioned, and he's significantly older than I am. So this was an even longer wait in some ways. He said Peter Garnovich was the third author on some of these papers, and George said he was telling Peter, you should do this for your thesis. It's only going to be another 40 years before you can finish the project.
Well, a 40-year PhD thesis, let's talk about that. Right, so with that,
let me mention something very quickly. I forgot to say, we just got approved HST, VLA, and Chandra observations. Follow-up, they will be happening 2019, 2020. So you'll be hearing from us again.
All right.
Awesome. I was going to actually ask for that, but before we get to the formal Q&A session, I would like to remind we have more than 160 people actually listening to us. I would like to remind everyone that recording of this and of all our webinars will appear on the AVSO's YouTube channel. So please subscribe. We're going to send an email reminding everyone exactly where this is, what the link is. And also please give us feedback through the survey. Remember to renew your membership. As Rich mentioned, we are a nonprofit organization. We are relying on donations, on memberships. And again, we would like to actually know that you are in our corner. We really, really appreciate the patronage of those who donate. And again, I would like to acknowledge Voice Astro that is providing some support for this webinar and help us bring you all these wonderful speakers and supports all the activities of the AVSO. So with that, I would like to actually start with a question that was actually asked after Michael's project. Michael, can people still observe your stars?
Oh, please keep observing. At least through October. I mean, the most critical stuff is observing period is probably gonna start to end maybe in September because we have to shift the light curves a little bit for the radio, but still through October is probably useful. And even having a little more of a baseline will still be useful for interpreting what's happening with the light curve, especially if we start getting near a peak or, you know, something weird's going on. More observations are always helpful.
Wonderful. Another question that came up, and Rich, maybe you can address that, is what is the exact difference between cataclysmic variables and symbiotics?
Well, I'll go from as someone without the PhD on here. The cataclysmics, correct me if I'm wrong, please, those are all main sequence stars that are have really close white dwarf companions that are increasing mass very rapidly, and that's why they have those frequent outbursts. With the symbiotics, they're much further out. So as Margarita mentioned earlier, the Roche lobe's not overfilled, but because these are evolved at this pace, red giant stars, usually those have some sort of outflow involved with them. And so that's where you get the accretion from. And so there is just a different dynamics going on between those type of systems, the dwarf novae. Am I on the right track here? Okay, great, because again, I'm a heating and air conditioning guy. I'm not an astronomer, unlike the people on this panel.
Lian?
I could add a short comment that there may be two kinds of symbiotics. They're classified into S and D types. The D types are dusty, and they almost certainly contain a Myra and already pre-existing wind and so forth. The S types have been suggested may be a little closer and may involve something close, more like a Roche lobe overflow. But they're both giants. They have a very cool star, and then they have some hot spectral lines that represent the dynamics in the system.
Oh, okay. Hey, I learned something because I didn't know that. And there's one thing, if you look at symbiotics, it's easy. If you look at a light curve and go, you can just say, oh, that's a Myra, or you can say, oh, that's a cataclysmic variable, like a SS Cygni type. Symbiotics, man, they're all over the place. There's no two light curves that look the same. I think these are very unique systems, and that's why I like to observe them, because they're so they're kind of, what's the right word, but they're a little different. They're all different. So they have their own personalities.
And even the ones that are classified as S, like for example CR6 has a lot of dust around. Of course, it's a giant, loses mass, and you have dust formation. But there is we need more observations, studies, and multivalent in infrared as well. As we have some colleagues, I at least saw one of the colleagues from Sofia, right, and ground-based mid-infrared observations, see what that dust is doing, how is distributed, and so on.
I think one of the reasons they aren't easily identified from a light curve is that they're classified by their spectra. Symbiotic meaning they have a cold thing, and they have some lines from something hot, and so it's two different things coexisting. Yeah. They're not defined by their variability, but by their spectra.
The cool thing about this kind of stars, either symbiotics or more classical CVs, although we have categorized them in specific groups for convenience, each and every one of them tell their own story. It's like you have kids, but each one has its own personality and its own kind of path. And at some point, you can always talk about kids, but you can't exactly group them. So that is what makes us all study these objects, and that's what makes variable stars so fun. You have to be open-minded. You have to keep your antennas up every time you observe them, because you never know what you're going to see. Even the periodic ones can surprise you from time to time. There's a question here about soft and hard X-rays. I think, Margarita, this goes to you. The detection of soft hard X-rays, are these along the currently known jet and clumps detected previously in our query?
In the X-rays?
Correct.
Our query, the Ara query jet has been observed, in optical, ultraviolet, X-ray, and so on, and including with Chandra in the last, wow, how the time goes fast, over 20 years, but the jet evolves. So the clumps, including the X-ray emission, have been observed before, but never in X-ray at the resolution that I showed you, because I do the convolution of the PSF in X-rays. So I have all the observations. I have the observations when we observed in 2017 in AVSO campaign. These observations, late 2019, 20, and we'll be having the coming ones. And they all have X-ray observations. And like in the other wavelengths, it's evolving. And I personally, I'm interested in how the jet evolves, but especially close to the binary. And we have resolved the binary. And so there I'm really focusing to see right where it is focused, where it is collimated. And so therefore the high resolution. And with the convolution in Chandra, we are basically reaching a Hubble Space Telescope resolution.
Wonderful. I have a question that I hear very frequently, and I get to answer very frequently, but I would like your take as well. And it says, with increasing numbers of automatic all-sky surveys, will amateur observations, especially visual, remain valuable? Who wants to go first?
I do.
Oh.
This is one of my big ones that we always talk about. Okay, so the surveys are not going to put us out of business, especially the visual observers. For one, surveys, if it says all sky survey, it may be that it is usually not all the sky. They avoid the Milky Way a lot of times. A lot of them really avoid the poles. And they also saturate most, you got to look at surveys. There's some surveys out there that won't observe anything brighter than 12th magnitude, which is really the range of where people with backyard telescopes really live. We usually don't go much lower than 12th magnitude. The other thing that you got to consider too, I touched upon this earlier, is the AVSO has those well-observed long-term trends that go back decades, sometimes even over a century. That can't be replicated by a survey. Most of the surveys have been around maybe a couple years, so they have really good data for a couple years, but it's all in different bands. There's no way, the traditional legacy information we have is all done by eyeball bands. And there's no real good transformation from a Sloan filter to your eyeballs, unfortunately. So there's no real good correlation to look at long-term trends. Now, photometric data tells you other things that visual data just cannot tell you. However, visual data is very relevant if you look at long-term time series. So that's really where we can have impact. If you're a visual observer, if you're looking at bright stars that are well observed, have a long observing history, those are where you should go. And those are going to continue to have value. Maybe the survey will overtake us in 100 years or so, but I don't think many people on the call are going to have to worry about that. I certainly don't think I do. Now, so keep observing, don't let it discourage you. And if you look at the LPV legacy program, that's really what it's built around. A lot of my predecessors spent a lot of time looking at what stars are really well observed, have great long-term light curves with many observers that are scientifically relevant. And so if you go back to our section webpage, download the LPV program, there's 338 long period variables in there. Those are the stars that the survey is not going to knock out. If you keep observing those, you're adding good work. And even some of those stars are probably not doing anything cool right now. That's probably going to change at some point in the next couple decades. You never know. I know it's not instant gratification. That's one great thing about like when people like Michael come on and say, look, I'm looking at these stars right now. There's some instant gratification. I know I enjoyed taking my scope out going, there's instant gratification here. Some of these other ones, it may not, but eventually if you look at the future generations, they're going to be able to have value from that work that you're doing now, whether you know it or not. So yeah, and the other thing you'll see a lot too with survey, oh, you got me going now. Surveys also have very regular cadence. They observe the same stars on the same, every so many days. Well, when people start looking at that and you start trying to do time series on that, you start getting a lot of alias frequencies in the Fourier spectrum, which throws people off. So if you'll see, I've seen this theme in a lot of things where people are going through the surveys, they do machine learning to figure out periods, and most of them are wrong until human eyeballs start looking at it and can not be fooled by the alias frequencies. We can learn what the real period is. And the other thing about visual observers or even photometric guys at this point, if we're not observing on very regular timescales, you can eliminate a lot of that aliasing. So yeah, visual observers are still relevant. We're still here to say there's a we're usually concentrating on brighter stars where the surveys aren't getting to, and we have that history which makes relevant data for long-term analysis.
Actually, this is a very good segue for the next question that I want to ask you. There's an individual who's asking, what is the ideal interval time for observing these LPVs, especially in the optical? How frequently, with what means, what do you recommend?
So the typical kind of standard answer, if you look at our observing manuals, will say, between 5 and 10 days. If you look at, Arnie has a equation out there to figure out the optimum, which is based on the amplitude. Basically, if you have a higher amplitude, you can go longer, sometimes 14, 15, 16 days. So for me, who don't have ideal sky conditions, it's whenever I can get out. And sometimes if it's been 2 or 3 days, yeah, I'll go ahead and observe a Myra again. If it's 14, 15 days, I'll observe it again. And hopefully, and that's another nice thing, if you really stick to the well-observed stars that are in the LPV program, if you look at our circular and see what other people are doing, you can find that somebody else, like say, for example, hey, I'm on a pretty bad run. It's been like almost a month and a half since I've been able to observe. There's other people that are picking up that slack and kind of filling in the gap for me. I do get sad sometimes when I make an observation and I look and it's been 2 weeks and I was the last one to observe it. I get sad. But most of the time that's not the case, where it may be 10, 14 days, but I see 1 or 2 other people have hit it in between that interval. So we're good. So yeah, with LPVs, you don't need to observe, definitely don't observe them multiple times in a night. If you're going every day, that may be a little excessive. You might want to look for more diversity. Every few days is fine. And if it has a real large amplitude, go ahead and stretch it out to a week or a week and a half.
Awesome.
May I just make a quick comment? Sorry.
Yes.
No, go ahead.
Margarita. Unless it's doing something.
Yeah.
Like when we had campaigns with the HST observations and so on, I mean, I had asked the observers, for Elizabeth, to observe twice a week, often if they can, before and after the observations, and especially if something is going on when you saw those sharp drops like in Sig. That goes fast. Whatever happened, the absorption from a jet, that goes fast. So the campaigns, the call, the alert notices are very important for the LPV.
Yeah. I should have put a disclaimer. What I was talking about, like a single Myra, those intervals I was talking about are fine. Now with the symbiotics, they are a little bit more eccentric and they do things like CH Cygni is a good example. If you're going to observe that star, ideally you would observe it once every night if you could, because you never know when it's going to do something. So the stars with companions are a different story. Every time you're out, go for it, do it.
Yeah.
Michael and then Leon.
Yeah, I just want to say for my Myras, which really aren't doing anything super exciting, they're just following their normal thing. Don't stress that you need to like get on them extremely often. They're, whenever you can, don't feel stressed. That's my big thing. I don't want people to feel like they really need to get on things or hit it really hard, especially like in one night. That's just not actually worth your time, really.
So would that be once every week or once every 3 days, or?
I mean, every few days if you want, or even a week, I'd be fine with, but I know AVSO prefers to do it a little more often what their recommended cadences are.
Cool. Leon?
Yeah, I agree with the previous speakers that 5 to 10 days, 3 to 10 days, somewhere in there is fine for most of the time. There are, of course, exceptions, and if you keep an eye on what's going on, for example, that last low minimum of our Aquarii, there was something going on a shorter time scale. When that happens, then you want to start filling in. and getting more frequent observations. There are some hints that some MIRAs near minimum might do something on a shorter time scale. If you're interested in that project, then that might be worth looking more often. Or if you see something that's anomalous, maybe you and some of your friends want to observe it more often and see what's going on, or more colors. But most of the time, 5 or 10 days works. And especially there is the factor that these are very red stars, so people's eyes are different. And so you do want some consistency. It's not always, 100 different observers, each with one observations in a cycle. You'd rather have some consistency of the same observers. But apart from that, 5 to 10 days sounds very good to me.
Cool. And now that you have the microphone, I have the last question for you, Leanne. The question is more fundamental about the nature of those objects. How one classifies an LPV star, either as Mira or V Aquila or something else?
Well, that's a messy kind of thing, actually. So the basic definition for a Mira is it's a very red star with a period, with a amplitude that is more than 2.5 magnitudes. And then there are the semi-regulars, used to be divided in 3 types, which is still somewhat useful. Those that were like a Mira, but the amplitude wasn't 2.5 magnitudes. Those that were like a Mira, but in terms of periods, but the cycles are more irregular, or those that are not actually the red giants, but are brighter, supergiants. So you had 3 different dimensions of departure from Mira in that classification scheme: spectral type and regularity and amplitude.
And go ahead.
If you go to the forums, I posted a forum post about red giant classification, and there's a paper on there that kind of talks about it, because we do classify them based, as Leanne said, based on their light curve, by their amplitude. It may not be a physical definition, so there's some people questioning, is a Mira really that different from an SRA evolutionary stage? And so there's some other suggestions that we do it maybe other ways based on whether they're multi-periodic or singly periodic. So that information's out on the website. If you want to check.
I might also add that there's a statistical method now. When you have a lot of these long period variables from, for example, the Magellanic Clouds, then you can do graphs of their periods versus their luminosity and classify them by where they fall in those graphs. And that at least fairly unambiguously identifies the mode of pulsation for each star, which has been otherwise difficult to establish on a star-by-star basis.
And we also kind of go further, because we'll define, Miras also by their spectral type, because you have M Miras and S Miras and C Miras, based on whether they're oxygen rich, carbon rich, whether that, they're in balance between carbon and oxygen. And there's also, when you look at those different definitions, they have different spectrum. Different lines really kind of stand out more than others. So there's some other physical stuff in that M class, S class, and C class is tied to evolution, or how long we've been on the asymptotic giant branch. Maybe
emission lines are also characteristic of Miras compared to some of the other types. Okay. Emission lines during part of the cycle.
Mm-hmm.
May I say just one related thing? It's Margarita.
Go ahead, Margarita.
Connecting to the outreach talk. These are long period variables. Get those young kids interested. We need them. These things, hopefully they will live over 100 years. We need young observers. So let's take them from the cradle if we can. But let's get the youngsters. I mean, the high school kids and the college kids, the middle school kids. Will be wonderful to get them interested. To participate and observe, and it was a fascinating talk about what Abby and others are doing. So,
the final comment to that is that it's never too early to start observing. So get your gear and your kids and your friends out and observe some of those objects. We are at the top of the hour, so I want to be respectful of everybody's time. Thank you so much for joining us today. Thank you to Rich Roberts, Abby Wagoner, Leah Wilson, Michael Stroh, and Margarita Karowska for a very interesting group of presentations and discussion following up. Thank you to all of you who have been listening to us and participating in the discussion. Next time, next Saturday, we're going to go on the other side of pulsation. We're going to talk about short period pulsations. Until then, please stay safe and have a wonderful rest of your weekend. Bye, everyone, and thanks again.
Thank you, Stella. Thank you, Rich.